بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. السلام عليكم everyone. First of all, رمضان مبارك، كل عام وأنتم بخير. يلا إن شاء الله help you through these difficult times, not because of the fasting but because of the exams. So يلا make it easy إن شاء الله for everyone. So let's start today inshallah by talking about the dynamics. So we're done with the kinematics part, which is the map that or maps or relations between velocities. So we had, for example, theta dot, which is velocity at each joint or velocity of each actuation that you have on your robot. And then how is this translated to other velocities? And all of these relations were completely kinematics, okay? And this, we also talked about the relation between the velocity and the pose, and this is what you all know. So for example, the h dot is equal to h multiplied by the v tilde, okay? So all of these are kinematic equations. We didn't talk about dynamics at all. When we talk about dynamic modeling, which is the topic of today, inshallah, we want to see the relation between these, the pose, the velocity, which is the generalized velocity or the twist, and the forces or the torques, or combined or the wrenches. So we want equations that will relate the wrench to the velocity and the torques and so on. Okay, so we want this dynamic equation. We already done that before when we talked about the rigid body dynamics of one rigid body, right? But now when we talk about manipulators, a manipulator is just a bunch of rigid bodies connected to each other through joints, right? And how do we describe these joints? We describe each of these joints by screw motion, and the relative motion between any of these two bodies will be just a screw in space. And we saw that we can combine all of these screws together with the exponential map, and we had the product of exponentials formula, and so on and so forth, okay? So today we're going to be doing just as a start, the dynamics, how to derive the dynamic equations of motion for a manipulator can be done in different ways. And you probably have seen something similar if you took any course on robotics when you did, for example, the Euler-Lagrange equation. Who here is familiar with Euler-Lagrange equation? Good. Well, I think everyone, okay. So the Euler-Lagrange equation, where you start with the kinetic energy minus the potential energy, you take differentiation with respect to theta or just the generalized coordinates, and you know how it works. We can do the equations of motion for a manipulator in this way, but you're not going to be learning anything again. So you're just going to be seeing some like epsilon of new stuff doing it this way. But I'm going to show you something completely different with the tools that we already learned, and how can we model a manipulator equation. Okay? This will also be important when we want to generalize later to something that's not fixed in space, but something that's also floating. So a floating based manipulator. Today, all of the lecture today will be completely written. The lecture of today is 2 parts actually. So we're gonna have this, today is the first part, and Tuesday will be the second part. So this is a very fundamental lecture, I would say. So I will urge you to all take notes as much as possible. Let's start by talking about just the motivation of what we're gonna be trying to do, okay? So when we talk about a manipulator, let's say, for example, something that looks like this. So this is up to n links, right? So this is link number 1, this is link number 2, and this is link number n. And the way we start, the first thing that you start when you see a robot like this is what? Frames, exactly. You should choose your reference frames. And the reference frames are completely arbitrary. With the tools that you learned, you're not bound to have the relative frames, or like having one frame related to another in some way. For example, like with the DH parameters, if you took that before. But we have full freedom in putting the frames as we wish. We just said that for simplicity, we can put the frames where the joints are. Today, when we talk about the dynamics, it will be useful to put the links at the center of the mass. Each one of these links, there is a center of mass, and it's a well-defined point in the object or in the link, okay? So usually the center of mass, we denote it by something that looks like that. And that's a particular point you can calculate precisely where it is on the body, okay? It's usually not the geometric center. What do I mean by that? So if I give you a circle, what is the center of mass? the center, right? This is the geometric center, not the center of mass. The center of mass will be exactly the same as the geometric center of this object you're talking about if you have a uniform mass distribution. If for example, if you have a circle, if you have this disk that is with the same material everywhere, so this is a constant, this is a uniform distribution of mass. But if you have a disk that has some mass on the right, for example, it's heavier on the left, so there's more mass than on the right, then you assume that you can imagine that the center of mass will shift a little bit towards the heavier part. So this is just where the center of mass is, and this is something that you get depending on the CAD model of your robot, if you have it, and depending on the mass properties and what the materials are, and so on and so forth. So this is a point that's well defined on the object. What we're going to be doing here is that what you can see as this multi-link robot, or this serial linkage, this open chain serial linkage, is in the end, we can boil it down to understanding what is the relation between one rigid body connected to another rigid body by one revolute joint, right? So in the end, it all boils down just to understanding having one parent object or one parent link and relating it to another link, which we're going to be calling the child. So this is the child of that. Why? Because they are both connected to each other by one joint. And usually, for simplicity, we're going to assume that this joint is a revolute joint, okay? Just for simplicity. Everything we do here is extendable to a prismatic joint by the tools that you know, with using the screw, like the screw definition of a prismatic joint or of a translational joint. But we're going to be doing everything with theta. So theta here means angular displacement. Theta dot means the angular velocity of the joint. It's not only that, because we're not talking about these rigid bodies moving relative to each other without any actuation. We also have an actuator there, okay? So usually we also assume that on the parent, there is usually an actuator that's that's fixed to it. So for example, if you have a DC motor, so the DC motor part, the stator will be fixed to the parent, and the rotor part of the motor will be attached to the child. So whenever a torque is applied by the motor, it rotates the child relative to the parent. Okay, so we also assume that we have here a theta dot of the child, and we have here a torque that's applied by some actuator. We also call it the torque of the child. Okay, so this is just notation. If we understand exactly what is happening here in terms of the dynamics, we can simply just replicate this from link 0 to link 1 to link 2 to link 3 up to link n. And this is the procedure we're going to be doing. So today's lecture, hopefully we can finish discussing what the dynamics of these two rigid bodies connected to each other with one joint looks like. First of all, how many degrees of freedom does this system have? No? Okay. Again? No. Okay, first off, if you have only one rigid body, how many degrees of freedom does it have? 6. If I have two rigid bodies that are not connected to each other, how many degrees of freedom do I have? I have 12, right? 6 for the first one and 6 for the second one. If they are linked together, what does this joint do? It reduces what? The degrees of freedom. In other words, it constrains, it adds some constraints. How many degrees of freedom does a joint have? If this is a revolute joint, it will have one joint, which means how many degrees of freedom did it constrain? 5, right? So it constrained 5. So I'll give you an example. If we say that this is a revolute joint and it connected in this way between these two rigid bodies, this means that these two rigid bodies can rotate like this with respect to each other. You agree? This means that they're not allowed to move relative in this direction, also in that direction. What's the third one? Also in this direction. So these are 3. And it's also not allowed to rotate like this. No, so this is the motion that's allowed. It's not allowed to rotate like that. And there's a third, like this, right? So it constrains 5 of the degrees of freedom. So 5 of the components of the twist will be 0 between these two, and only one of them will have an angle that you can apply. If it's actuated, then this angle is actuated by some torque or something. Okay, so you all visualize the picture. Is that clear for everyone? Now let's look at, with only the tools that we learned. Okay, so a joint, capital adjoint, small adjoint, exponential map, everything. How can we describe the dynamics and reduce this and talk about how they look like? Okay, so 6 plus 1 degrees of freedom. Okay? Because this one by itself, first of all, this is not connected to anything. Okay? So this by itself has 6. When you connect to another body, okay, and it has a relative motion between them, then you can only apply 1 extra degree of freedom, which is this angle. But this, and that's it. So it's only 6 plus 1. It was originally, you can think of it this way. So the 6 plus 1 is equal to 7, right? Originally, it was 6 plus 6 because we have 2 rigid bodies that are not connected. And then you had 1 joint, and the joint constrained how many degrees of freedom? Constrained 5 of the degrees of freedom. Okay? Then you were left with 7 degrees of freedom, which is 6 plus 1. Clear? Yeah.
So the whole system, like both rigid bodies together, they can translate, they can do whatever.
That's right. Yeah.
But then there's an added angular restriction that brings about the additional one.
Yeah, exactly. Exactly. You need to provide the information about where this object is, and you need to also provide them the information about the relative angle between them, and then you can talk about where this object is in space. The picture that you have there, of course, is not this one. How do we make this one to that one? You first connect the parent, right? Assume that this is the 0 one. We connect it here by another joint to the base space, or to the stationary frame or the stationary base, the base of the robot. And then you keep on adding here. So this will be link 1, this will be link 2, and then you add link 3 up to link n. Okay, so we're going to be seeing how recursively we're going to be building this in a tree model.
Instead of fixing it to a base, cancel out to the 6, and then it's reduced to 1.
Exactly. If you add another link, add another joint here, then the 7 will be reduced by 5. You're going to be having 2 degrees of freedom. And this is the picture that you imagine, right? So if I give you this robot, for example, and I ask you how many degrees of freedom does it have? It's only 2, right? Theta 1 and theta 2, right? So it was 6 plus 6, and then I had 1 joint and 1 joint, each of them reduced 5 of its own. Then I had 12 degrees of freedom minus 10. I'm left with 2 degrees of freedom, theta 1 and theta 2 here. Okay. Now let's look at this parent-child dynamic model. Okay. So what we're going to be calling the parent-child model. Okay. And this is only a building block, as we said. We're going to be using it recursively in a way, as we're going to see. Let me just draw the picture again here. So, alaikum salam. So this is the picture we just talked about. We have a parent link, we have a child link. Both of them are connected by 1 degree of freedom joint. We assume it's a revolute joint, so it's actuated by some tau, and it has an angle called theta, or an angle of velocity called theta dot. Okay, we're just going to call it theta dot. And we have an inertial frame, that this inertial frame, we're going to be calling it frame 0. It's locating somewhere. So the rigid body dynamics of each of these two, so the rigid body dynamics, right, you should be familiar with that, is that we have the generalized inertia tensor of the parent expressed in the parent frame, multiplied by the twist of P with respect to 0 expressed in P dot. Right? So this term is the rate of change of the body momentum, of the momentum in the body frame. We had the adjoint term, which had a combination of all gyroscopic and Coriolis effect, which is this one. And then what are the external wrenches applied here? So this equation simply says that the rate of change of the spatial momentum is equal to 0, right? So momentum is conserved. If we have external wrenches, then we get here external ones. Let's assume there is no gravity for the time being. What is the only wrench that's applied on the parent body? Due to the child, right? If the child starts to move around, it will like push the parent body. We're going to be calling this wrench that's applied by the child on the parent, expressed in the parent frame, we're going to be calling it like this. So it's denoted by wrench of C applied on P expressed in P. Just as this is very important to denote. When we talk about a twist, we say how many indices does a twist have? By definition, it has 3 because it's a relative twist between frame A, which is the index down, with respect to frame B expressed in a third frame C. When we talked about the wrench, how many indices did we give it? We give it only 2. We said this is the wrench applied on a body, right? Expressed in some other frame. So here we're talking about the wrench applied on the body P expressed in the P frame. We just denote here that this is the wrench that comes from a source. What source? What kind of source we're talking about? We're talking about the source of frame C or body C, okay? Just to be clear. Yeah. This is the last thing we're going to be doing. Yeah. Just be patient. Okay. So this is the first equation. The second equation, we're going to have something exactly the same, but for the child. It's exactly the same. We have the generalized inertia of the child expressed in the child frame. We have the rate of change of the child twist expressed in the C frame. We have the adjoint VC0, ICC. What about the wrench here? What is the wrench applied to the child? The wrench of the parent, exactly. Because the parent, when it starts to move, it will move with the child with it. So this is the wrench that comes from the parent. So this is the source. In which frame will it be applied on what? Applied on the C frame. Expressed in what frame? It has to be expressed in the C frame because everything here is expressed in the C frame. So everything in this equation is expressed in the P frame. Everything here is expressed in the C frame. Did we choose where the C and the P are located? These frames? They're completely free. Right. This is something very powerful about this equation and something we didn't have time, but it was mentioned in the book if you want to have a proof. That this equation will remain always the same no matter what frame, what body fixed frame you choose here. So if I choose the P to be on the center of mass or not on the center of mass or even outside of the body, but still it's rotating or moving with it, so it's always a body fixed frame, then the equation will always look like that. That's not the case when you have, for example, an equation in terms of the angular velocity alone and the linear momentum alone. You remember the one that you derived in the assignment? This is only when you express it in the center of mass that you have these two separations. But in general, you have this equation, and it always looks like that. Okay, so this is known as a form covariance. That it means that no matter what frame I choose to represent it, it always has the same form. So it's invariant to coordinate changes or invariant to frame changes. This expression. So this is the first thing. Any questions? Okay, this should be familiar. Now let's go to the joint. So part B will be about the joint model. Unfortunately, I have to draw it again. Can I copy? Let's see. Let's see. Okay. Now what? Nope. Okay. For safety, I'll draw it again. Okay, so this is P. That's it. Okay. Uh, the relative orientation. Sorry, the relative pose between the child and the parent frame is a function of what? Is a function of theta, right? You all agree? Does anyone know what a very quick expression to do it? The exponential map, exactly. So the exponential map, if you represent this twist, okay, so the screw axis, so the one that we have here. So this screw axis is of the child body with respect to the parent body, and I can express it in many frames. I can express it either in the C frame, I can express it in the B frame. These two frames, and I can express it in any other one. These two screw axes are very special because they are constant. No matter what the object will start to doing, these two frames, so these two screw axes will always be fixed in the C and the P frame. So they are constant. They don't change. It's only if I relate them, for example, to the zero frame, then you start to have an adjoint and it will start to give it some some angle dependency. But in general, these will be fixed if you represent it in the C and the P frame. I can calculate this relative pose using either one. I can use the one that we introduced in the lecture before was the CPP multiplied by theta C. And then I have here HC with respect to P in the zero frame. Is this familiar? Right? So this is the exponential map. You can show, I'm not going to do it, but you can show for yourself, and it's very easy to do it actually, that this is also equivalent to HCP from the left multiplied by the exponential of SPC with respect to P expressed in the C frame multiplied by theta C. Okay. So this one is expressed in the P frame, and this one is expressed in the C frame. Okay. And it's just a pre-multiplication or a post-multiplication by the constant transformation. So this is something very easy to program. And in the next assignment, inshallah, we're going to be doing this on MATLAB. It's very easy. Right? You just need to program the expression of this, which had on the rotation part the Rodriguez formula, and on the translation part some extra terms that you can easily calculate by taking the skew symmetric form of the translation part and the rotation part, blah, 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 blah. It's something very easy. And you just give it the constant transformation at angle 0, which is something that you choose. What is the angle 0? What is the home configuration? What is the angle at which these two are aligned or not aligned? It's up to you. It's your choice. And then for any given angle, you can calculate the relative pose like that. What about the angular velocity? Sorry, what about the twist and the relation to the angular velocity, which is theta dot? Okay. If you talk about the relative twist between C and P expressed in the P frame, then it's simply SCP P multiplied by theta C dot. If you talk about VCP in the C frame, then it's equal to SPC and multiplied by theta C dot. It's as easy as this. This is all of the information you need. And again, it's something very easy to program, right? Because these are constants. How are these two related to each other? So these two are related to each other by what? By the adjoint. Adjoint of what? The joint. So I can calculate, let me write it like here. So S, where is it? Yeah. C with respect to P expressed in the C frame is related to the S of C with respect to P in the P frame by the adjoint of P with respect to C, right? As a function of theta or as a function of 0? As a function of the 0. Right. Why is that?
Again, you can prove it for yourself that if I apply here the theta, so h of p of c of theta, which is the inverse of that one, that it doesn't matter and only this part will stay and it will affect here. So you can show it yourself. Another way to think about it just intuitively, we said that both of these are constant, right? They don't change with the angle. Okay, so this is why they are only related by the constant transformation between the C and the P frames, okay, and the C and the P links. So this is all of the information that you have on the joint. Okay, so you see the joint, okay, so the joint is only defined by one thing, which is the screw axis, right? And then everything just follows. The relative pose between the two bodies that are connected through this joint follows from this equation, and the relative twist between between the two bodies connected by this joint follows from this equation. Now we're gonna write a very important equation, which is remember we said that in terms of the degrees of freedom, that this one has 6 degrees of freedom. When it's connected to that one, how many extra degrees of freedom do we have? Only 1, right? So the whole system has only 7 degrees of freedom. Which means that the VC, this expression, if we calculate it, VC with respect to the inertial frame expressed in the C frame, which is the generalized velocity of the child link, right, with respect to some stationary frame. So this expression, let's calculate it and see what does it look like. From the equation that you proved yourself in the assignment, this we can write it as the relative twist between the P and the 0 plus what? So something expressed in C, everything here has to be expressed in C. What are the two indices that has to be here? So this is a question for the exam. C down, P up. Everyone agrees? So the C with respect to 0 is the C with respect to K and K with respect to 0, right? And I can add all intermediate ones. I can write here, for example, M and J, and they all have to cancel out in this way. And you had something like that in that sign. What is this expression? So this expression, I can write it as the adjoint of VP P0. What are the indices here? Who's down? P and C up. Plus, what about this expression? I can write it by the theta dot there, right? So I can express it like that. Okay. What does this expression say? First of all, we have here, this is a function of theta C. Okay, so this is not the 0 one, this is a function of theta C. What does this expression say? Okay, can someone read it and just try to figure out? It's a map that takes what and outputs what? It takes the angular, the generalized twist of this body. How many degrees of freedom does it have? 6. And it takes also on this side what? The angular velocity of the joint. How many degrees of freedom of that? Is 1. And what does it produce? VC with respect to 0 expressed in C, the child twist. Which means that if I say where the child is, where the parent is, or in other words, what the velocity or what the generalized velocity of it is at a certain moment. And then I also specify what the theta dot is, then this velocity or this generalized twist, the generalized velocity or the twist of the child becomes identified. Right? There is no more degrees of freedom. And this is what we mean here by this, that both of them together, if they were not connected, we had 12 degrees of freedom. We had degrees of freedom for this one, which are the 6 of the P frame, of the P link, and 6 of the child link. But when they are connected, this equation already says that I only have 7 degrees of freedom in this quantity and this quantity together. And together, I get the child twist. Okay. Let's keep that for now because we're going to come back to it later. Let's see. Okay, let's go back to this expression. Again, through the joint. Are these two wrenches related to each other? So these two wrenches, are they related to each other? So if I'm pushing on the wall and the wall is pushing on me, are these two forces related to each other? They are exactly the same magnitude and opposite in the direction. That's Newton's third law, right? So the generalized way of writing Newton's third law in terms of wrenches is as follows. We have that, let's write it here. We have that the wrench of C applied on P is equal to minus the wrench of P applied on C. But they have to be expressed in the same frame. So this has to be in the star if this is in the star frame. If we want to relate, if you want to calculate this one, which is the wrench applied expressed in the P frame, then the wrench of C applied on P expressed in the P frame will be equal to the wrench minus the wrench of P applied on C expressed in the C frame, which is that one. What is the transformation between them? The adjoint transpose. And we have here an H. What about the indices here? Again, an exam question. What is down? No. PC. Again, the easy way to think about it. The easy way to think about it is just an easy way. It has nothing to do with matrices. It's just an annotation trick. The transpose, you can imagine that it flips the indices. So this, again, so this is in C, then it should have a C down and a P up, but this is a transpose, so the C will be up and the P will be down. This is just an easy way to memorize. So we have this expression between the two wrenches. Okay. So now the two wrenches are related to each other. The two twists are related to each other. It all makes sense, right? The last thing is that, what about the torque here? Is the torque that's applied as an actuation, is it related to these expressions? But it's related to the wrench. By how? Now let's look at the duality equation, which is this one. You see this equation? Let's look at its dual. What does duality mean? Duality means that whatever we multiply here by the theta dot to give power, right? Which is in this case what? The tau. And what is the object when we transpose it, or when we take the duality product with it, that with the twist gives us power? It is the wrench. And expressed in what frame? It has to be expressed in the same frame, in the C frame. And then we should get some relation between the wrench and the torque. Okay, this expression, you can see it for yourself that just by duality, it has to be that's it. So this is for any wrench. This is very important. This equation is for any wrench. Any wrench that you have applied on the C frame, okay, on the C body, expressed in the C frame. If you multiply it by the transpose of this screw axis, will give you whatever torque this wrench corresponds to. For example, if I have here a wrench due to gravity, and I want to see the corresponding torque due to gravity, I multiply it like this. If I have here some wrench due to interaction with, I don't know, with the environment, and I want to see what is the corresponding torque, then I also use this expression, and so on. So this expression is simply the dual of the one on the top. And you remember when we talked about the duality, okay? So this is a map that goes from one number to 6 numbers. The transpose will take 6 numbers and will give us 1 number. You see, this is the dual of this map. Okay? So this is a linear map, and this is the dual of this linear map when we talked about it earlier. Yeah.
That's just like the Jacobian, but just for a single.
This is the Jacobian, yes. That's exact. This is what we talked about to be the Jacobian, yeah. And this is the Jacobian transpose, yes, exactly. Now we're going to be doing something very, very interesting. You see now the joint in the end. What does it do? The joint relates the two wrenches applied between the parent and the child to each other, relates the relative twist, or in the end, the twist, sorry, the velocity, the twist of the P frame with respect to the P body with respect to the zero frame, and the C body with respect to the zero frame, relates it also to the angular velocity. So I have this second relation, and we have a third one that relates the wrench to the torque. Okay, all of these three equations together, I'm going to write them in a very special form as follows. Okay. The three equations we just wrote are written in this expression. Okay. You need to expand it and go back and forth between it, okay, at your own pace, okay? If you cannot see it now, okay, that's okay. But this is precisely the same three expressions we had. So the first one simply says that it's related to this. So all of these dots here, it means zeros. Okay, so all of these are just zeros. So this expression, so this wrench is equal to this expression multiplied by that wrench. So this is the relation between the two wrenches we talked about. This, the child twist is related to the P twist and related to the theta dot by the second line. And the third expression says that the torque is equal to the transpose of the screw axis multiplied by this wrench. In the end, everything in here, again, how do we calculate the HPC with respect to theta C? With the exponential. What does the exponential need to have? It needs to have this expression. You see SCPC, which is also here SCPC. SPC, CPC. So everything here in the end is just a matrix that we're going to be calling it the joint matrix or the joint transformation. It's just one big transformation that is only a function of theta C. Okay? And it takes as parameters, as constant parameters, the SCCP. Because everything, the H here I calculated with the exponential map. Okay? And that's it. So you see, this is everything what the joint does. This is, of course, an ideal joint. This is an exercise for you to try at home. Try to prove that when you multiply or take the duality between this guy and that guy, plus this guy and that guy, plus this guy and that guy. Remember what duality does? What's the duality between angular velocity and torque? What do you get? What's the duality? What's the pairing? What's the multiplication of torque and angular velocity? What's the units of? Power. This is Newton meter. This is rad per second. You get power. What about twist and wrench? The twist had angular velocity and linear velocity. The wrench had torque and force. What is the pairing between these two? Also mechanical power. What about the wrench and the twist? Also power. So in the end, the equation that we're going to write here is simply the power balance of this joint. It says that this is the power that you supply by the actuator, right? Because you move this, you apply a torque by a motor, right? And the link starts to rotate by some theta dot. So this is the power applied by the motor, by the actuator. This is the power that goes to the child. and this is the power that goes to the parent. Okay. So in the end, the picture that we have with the dynamics of all of the dynamics, the coupled dynamics looks like this with this definition now. We're going to have this way of writing the dynamics. So this is the coupled dynamics. I think this will be C. So all of the coupled dynamics in the end looks like this. This is just a pictorial way of the dynamics. We have the parent equation. We have the parent dynamics, which is expressed in the P frame. What this equation takes, we go back here. So what is the input to this equation? The wrench, right? If you supply the wrench, it will take, again, it will calculate the V dot. Of course, it's a differential equation because it's a function of VP. So it's like it integrates the V dot and then takes it back. You remember how we drew it before? So this is a differential equation in VP. So in the end, this is an equation that takes the wrench applied by the child applied to the parent applied in the P frame, and it will output VP with respect to 0 expressed in the P frame. Then we have the joint. And the joint here is this expression we just talked about. Theta C. We have here as an output the torque, as an input the theta C dot. What is the output of this? So again, so you look at this expression here. So theta dot is an input. WPCC is an input, which is what will come from this side. And then VP P0 is an input, which is this. And then we have here as an output. Oops. We have B, C, C. We have that one as an input. And then it goes to the child dynamics. But the child dynamics here are not used in the same way as the parent dynamics. They're the same equation, but they are used differently. Because in this equation, I have the wrench as an input, and I calculate the V dot, so the VP dot, and I integrate it. But this equation, I take the VC, and then I differentiate it, and then I use it here in the child dynamic. This is why the child is called an inverse dynamics equation. It's an inverse dynamics. So because it takes the twist as an input and the wrench as an output. How does that work here? To go back to this expression, you see that in the child equation, because of the joint and because of the relation that we had between VC0 and C and the VP 0P and the theta dot, which is given by this expression, you see the VC0C is just determined. There are no more degrees of freedom. I cannot calculate it with anything else. I already calculate everything here. So that's why it's an input to this equation. So this is an input. So this is an input. What about this one, the V dot? I differentiate the VC and I get it. Then everything here becomes known. The only thing is unknown is this expression, which is the wrench of the P applied on the C expressed in the C frame. No.
If the BCC is known already.
This one, yeah.
Because that's what we're getting from the other equation.
From this equation.
Exactly. So when we go back to the other one, and it's already known, then is it still reasonable for us to call this a differential equation particular?
That's why it's called a differential equation, but what's known as in differential causality. This is what's known as integral causality, because you solve this equation by integrating the variable, but here you solve it by differentiating this variable. That's called in differential causality, something that's not usual. By the way, everything we're doing here, we're going to see in the end where does it boil down to. Okay. So this is everything that we have. So this is the dynamic equation, you see. So I had one equation for the parent, one equation for the child, This one is in normal causality or in the integral causality, or it's just the forward dynamics. This one is in the inverse dynamics because it's, you see, they work differently. And then this is the part that goes inside. Okay, this is what I supply to the joint by an actuator, and I apply theta dot here, and this is the equation. This is what's known, this is the very, very ugly way. Again, this doesn't work in the computer, by the way. There's a lot of problems for it. This is only we're writing this in this way because we're going to be using this inverse dynamics part as part of an algorithm to try to write the manipulator equations in the end. So this is only a stepping stone for us to use to derive the actual equations of motion. Okay, because this is not usable at all. Okay? And this is known as the Newton-Euler inverse dynamics. Okay. Okay. Let's see. Okay. The last thing that we need as just as for this to work is the V dot. Okay. The V, we have a closed form expression to it. Can we have a closed form expression for the V dot so that we can plug it in this expression? Yeah, let's try it. Let's see if you know everything about it. So the V dot here, so the VC dot is equal to the time differentiation of the adjoint multiplied by the V dot. Sorry, multiplied by the twist. So I have a differentiation of this part plus multiplied by that, plus the differentiation of that part multiplied by that. You all agree? So I'm going to have like something like the time derivative of this. The time derivative of that, you should be familiar that it looks like, where is it? Yep, you're right. Let's see. Too many pages. Okay, so let's have this. So this should be equal to the adjoint of HPC. I'm going to just drop the theta dependency, multiply by the adjoint of V. This has to be in the PPC. Yeah. Multiplied by VPP0. Hope that's correct. Then we have the adjoint of HPC. Okay, it's actually the same as the one outside. I'm just going to take it for both. Then I have here the VP P dot. Then I have the time derivative of this multiplied by that plus the time derivative of that multiplied by this. What is this term? Constant, so it has no time derivative. It doesn't change. So in the end, I'm just left with this expression, theta double dot. Yeah. Let's see. Okay, let's just keep it for now. We can simplify this a little bit, but we're just going to keep it like this, okay? Maybe next lecture we're going to simplify it so that we can move on, or let's see at least when we need it. Yeah, okay, that's it. This is everything we need to have to talk about the dynamics. You see, I have a closed form solution or closed form expression for V dot, closed form expression for the V, and they depend on the theta dot and the V. And of course, this one is an acceleration, so it will depend on, you see there's an acceleration term here. There's some adjoint between the two twists. So you can imagine that this adjoint of two twists gives us something like an acceleration. And we have here an acceleration term, okay, in terms of the theta. That's it. So we're done. Of course, it's not satisfactory because you didn't see anything. Now let's just apply this to some of the simple examples that we're all familiar with and see whether we can, by taking this building block and try to make out of it something more complicated or something very simple for examples that we're all familiar with. The first one is just one body attached to a stationary frame. What does this look like? A pendulum. pendulum equation. And the other one is a two-link robot arm connected to here the stationary one. Okay, so we're gonna do only the first example, which is just the pendulum equation. So now let's use this picture and try to reduce this to the pendulum equation, to the pendulum dynamics. So in the pendulum, we have something that looks like this. So we have one link. Okay. There's a center of mass here. For simplicity, only for simplicity, okay? Not because of any limitations of the algorithm or of the method. Let's put the link frame at the center of mass in this picture. Okay? And then we have here, so this is the theta. Again, so the theta actually is just, again, you can imagine in what we're talking about. So here, yeah, so it's rotation about this one by, so this is the theta 1, which is the same as, again, imagining it like this. You all see that? Okay. So when this pendulum is in the downward location, which is in this picture, and this is the zero frame. So this is how the zero frame looks like. So this is the x hat of the zero frame and the y hat of the zero frame. This is the x hat of the one frame. This is the y hat of the one frame. This is our home configuration. This is what we call theta 1 equal to 0. So this is our home configuration. Everything will be built from there. Okay? Is that clear? So this is exactly what we did. But now with the picture that we had, so we're assuming here that the P frame and the zero frame are the same thing, right? So if we go back to the picture that we were working with, which is this one, we assume here that the P is fixed. It's not something that moves at all, right? This is like the base. And only the child is moving, right? So the P frame is nothing else than the zero frame here, which also means that the VP with respect to 0 expressed in the P frame is what? 0, right? The two frames are the same thing, right? Or they are connected to the same body. There is no relative motion between them. There is no P frame, right? So there's no P body. There's only one body, which is the child here. So if we write the equation of motion of the child, which comes from the dynamics, you can find out it looks something like this. So this is exactly the same expression that we had in the first part for the child. We just wrote it as V and V dot as an input, so on the right-hand side, and the wrench as an output. We wrote it in a differential causality, right? So in the inverse dynamics equation. I replaced all of the C's by 1 and all of the P's by 0, right? Because the P here is the 0, and the C, right, is just the 1 link, okay? So this is the child to have. So this is the equation that we have. What about, any questions? Because it was on this, this was on that side. So we had that the I dot, IV dot, is equal to the adjoint transpose plus the wrench. If you bring that on the other side, it becomes a minus. Bring this on this side, this becomes positive, this becomes negative, and then you swap what's on the left-hand side and the right-hand side, just swap them together. So here in this part, then we have that we said that the V1 with respect to 0 expressed in the 1, which was the C0, right? PC. It had two terms. We go back here. One which was multiplied by the VP, 0P, which is in this case what? 0. So this term drops and we're only left with this term. Okay. So we have here, this is equal to S1 0 theta 1 dot. What about the v dot, v1 dot? All of the other terms, they just drop because the vp0 p is equal to 0. So we just left here with s1 1 0 theta 1 double dot. What about the torque? So the torque that's applied on this pendulum, okay, so this pendulum, there's a motor here, right, that supplies some torque that makes it move, right? So there's an actuation here. So we have here tau 1 is equal to S1 1 0 transpose multiplied by 1 1, the wrench. So that's the equation. So these are all of the equations that we have. Of course, everything is simplified because we just removed the parent frame. So now let's combine all of these equations together. So you see here that tau 1 is equal to this expression multiplied by the wrench. The wrench is given by this expression. V dot is given by that expression, and the V here is given by that expression. See, everything is easy, hopefully. Let's look here about the inertia. So we just need to look at the inertia for a moment. The inertia here, the generalized inertia of this object, which is of 1 here. So the generalized inertia of this link expressed in the one frame. What does it look like? This is the center of mass frame. So we said that it will have some J here and some 0 here and some 0 here and some M multiplied by the identity. So this is the mass of the link. This is not the usual pendulum you're used to, right? The pendulum you're all used to has one assumption. It says that it has a link that's massless, and there's the center of mass is at the point, at the end here, right? You're familiar with this picture? This is not this pendulum, this idealized pendulum. This is an actual pendulum where there's just one rigid body connected in this way. Okay, so the center of mass here, you can think of it, this is where the lump of the mass is. But an extra thing that this body has that a point mass doesn't have, which is the J part. Okay? That's why it has a J and the mass. We're talking only about a point mass that's at a distance, right? The standard pendulum is just M. It doesn't have any inertia. Any rotational inertia, of course. Let's see. Okay. Now I'm just gonna take these expressions. I'm gonna write them all. I'm gonna take all of everything here. I'm gonna put them in this equation. Okay. So I'm gonna write tau 1 equal to the left hand side of everything. Let's see what this looks like. So this is tau 1 equal to S1 transpose multiplied by, then we open bracket. We have here the I11 multiplied by S10 multiplied by theta 1 double dot. So that's the first expression. Then we had the minus here. S1 transpose multiplied by the adjoint of yeah, that's it. Okay, I just removed the V dot. This expression was V dot, was I V dot. I wrote it in terms of the theta double dot. This expression, that expression where the V, right, 101, I wrote it in terms of the S101. This expression is very interesting, and this is a property you should all like memorize, and it's very easy to prove. If I first of all, let's transpose this guy. So I'm gonna write it as adjoint of S110 theta 1 dot multiplied by S10, and everything is transposed. Okay, so this is A transpose multiplied by B transpose. So if I transpose both of them, then this will be B transpose BA, all of them transpose. You see it? Okay. So I have this expression here. The adjoint is a linear map. Okay. Does anyone remember what a linear map? Something we started with the course with. What one of its properties? A linear map F, if it's a function of some lambda multiplied by x. So x is a vector and lambda is a scalar. What was this equal to? Lambda f of x, right? So if this is a linear map, and you can prove it for yourself that it's a linear map, we can take the theta dot outside. So it looks like this. So this is equal to theta 1 dot multiplied by the add of S1 0 multiplied by the S1 0, like that. Okay, so this is the add of S of some twist or some twist with itself. You can prove for yourself that any adjoint of two twists that are the same will give 0. It's very easy to check it out. Okay. If there's time in the end, I can show you very quickly how it looks like. It will just take a couple of steps. Okay, but for now, just leave it like that, okay, so that we can continue. So this expression now just all drops out, and we're left only with that guy. So this one is equal to, I'm gonna write all of these three terms, I'm gonna write them as 1m. So this is a constant, this is a constant, and this is a constant. Everything here is a constant. What is the dimension of it? Let's check. This is the dimension of the S is what? 6 by 1. What about the inertia? 6 by 6. What about the S transpose? 1 by 6. So 1 by 6 multiplied by 6 by 6 multiplied by 6 by 1. And then gives you 1 by 1, which is a scalar, we call it m, multiplied by theta 1 double dot. Let's check what this expression looks like, what the m looks like. If you take this expression, okay, so this expression of the I, it's something very easy to play around with. Expand the j such that it looks something like this. jxx, jxy, z, y, yy, yz, yz, zz, xz. Expanded like that. So what I'm trying to say is that keep this completely populated. Don't assume it's diagonal or anything, okay? The most general thing. Of course, it's symmetric. It has to be always symmetric. So keep it like that. And then multiply by the I by the S, which in this case, we haven't defined it yet. So what is the S? This is the only thing we need to define as a constant here for this to work out. What is the S of 1 with respect to 0 expressed in 1? So S of 1 with respect to 0 expressed in 1. So this is the screw axis we were talking about. We want to express it in this frame. First of all, we said that this is the x, this is the y, and this is the z. So this one, it has two terms. It's a revolute joint. So it has an n hat and some minus n hat cross product with some point on the axis. Of course, seen from the frame one. What is the n hat? The n hat is 0, 0, 1 because we're rotating around the z-axis. What about the point Q? Which point do you wish to choose on this line such that it's the easiest to work with? Let's give, okay, we didn't give any dimensions here. So let's say, for example, that the length of the whole link is L, and this center of mass is at a distance of L over 2. So capital L over 2. This is the x hat 1, and this is the y hat 1. So what is this point? It is L over 2 in which direction? In the minus x1 hat, right? So it's minus L over 2, 0, 0. Clear? Okay. So take this, okay, so now this twist, after you do the calculation of the cross product and so on, you can show that it looks like, where is it? Okay, it looks like this. So 0, 0, 1, 0, L over 2, 0. Okay. So 0, 0, 1 is the n hat. And then when I take the cross product of this n1 hat, of course, with a minus, with the q1, which was in the x. So I have x and the z. I get something in the y. This is something you can always check very quickly, right? You all know that you take the cross product of something in the x and the y, you get in the z. You take in between the y and the z, you get in the x. You do between the z and the x, you get in the y, right? So this is an x, a z, I must get it in the y. So this is just a sanity check whether it was correct or not. Of course, it can be right or wrong depending on the minus sign. So this is where you need to make sure it's correct. So this is our S. Now, what I'm saying is that multiply this S transpose by the inertia tensor by the S. In the end, you're going to get this M. This is your homework to try out for yourself. The M will be equal to JZZ plus ML over 2 squared. What is this expression telling us? What is this expression? Parallel axis theorem, exactly. This is nothing else than the parallel axis theorem, right? We have here, to go back to the picture, our picture was something like this. So we had here a lumped mass. So this was the center of mass. Okay. But this also part, it has an inertia, right? Inertia around this frame. Okay. So if I rotate around this frame, I have some inertia, which is the JZZ, the rotation around the Z axis. It's the only thing that affects here the motion, right? Because everything else is constrained. I'm not allowed to move in any other direction except in this one. So in the end, after I did all of these simplifications, this is the reduced dynamics. I have only, how many degrees of freedom does this system have? Has only 1 degree of freedom, right? I had one rigid body in the start, which was 6 degrees of freedom. I constrained 5 of them by the joint. I'm left only with 1. So I have only an equation in a scalar that says that theta double dot multiplied by some inertia. This is a rotational inertia. I write it here by M because this is in general. This is in general a mass matrix. You're going to see why we call it a mass matrix next time, inshallah. So this is a mass matrix, or in this case, just a scalar, an inertia, and equal to torque. So torque is equal to inertia multiplied by theta double dot. Nothing fancy, nothing new here. You all know that. Okay. Okay. There are only 5 minutes left, but okay, let's stop here. Okay, so we can continue now because we didn't add the gravity here. So we can add the gravity in 2 ways. Okay, one is very familiar to you. You say that this object or this frame is stationary. So this is a stationary frame. The gravity, let's assume it's in this direction. What about the gravity force? What about the gravity force? What does it look like? Where is it applied? At the center of mass. So I have here a force, which in the end is, I can make it into a wrench. I have here a force that's mg. So I can have a wrench applied on the child frame, on the one frame, on the one link. Seen in the one frame, it will have, okay, I can work out what does it look like, right? And then I transform it back into a twist, sorry, a torque by multiplying it by the S, right? You remember what we said here? In this picture, we said that the torque is equal to the S transpose multiplied by any wrench here. So if I put here the wrench due to gravity, should be equal to that red one. I'm gonna get here an extra term here, which is the torque due to gravity. And you're all familiar that this gravity in the end should be equal to the torque due to gravity, should be equal to something like mgl over 2 sine theta 1. If you did any pendulum dynamics at any point, you should have seen this expression somewhere. So after doing all of that, we should get this expression as an extra torque. Next time, I'm going to show a completely different way to get the gravity. Okay? We're going to be treating gravity in a completely different way by what's known as the equivalence principle, okay? Einstein's equivalent principle, something completely new to you. But in the end, you're going to get the gravity term, but even it will, the next time what we're going to be showing is a general way to get the gravity, even when you have a multi-link rigid body, or multi-link manipulator, sorry. Okay, just 2 minutes left. Let me show you very quickly this part. Okay, so let me show you why is that when you take the adjoint of something with itself, you have to get 0. So let's assume that v is equal to omega v small. Okay, so omega is an angular velocity, v is linear velocity. The adjoint of v itself was a 6x6 matrix that looks like this. Where was the v? Does anyone remember? Down, right? Okay, this is a 0. What about the add of v with itself? Then we have that this is omega v, and this is 0, multiplied by omega v. Work out the expression, you're going to find that this is omega, this is v, omega, omega tilde V. The first expression is omega cross omega, 0. Second expression is V cross omega minus V cross omega, which is also 0. Okay. So the adjoint operation between any two twists, okay, of course the same, you always get a 0. Okay. And this is why we have this expression was 0. That's it. Okay. Any questions? So now okay, so just let's recap very quickly. So this is a very fancy way to derive the pendulum dynamics. Okay. Of course, we're not doing this to derive the pendulum dynamics. This is just showing you that this is a very general way to derive the dynamics once you reduce it. Okay. So what I wrote here is the Newton-Euler inverse dynamics. Okay. And you need to reduce it. Okay. So you need to reduce down depending on the constraints. So what happened here is that we wrote all of the equations in terms of the tau and the theta dot. Okay? So you can imagine next time when you have a number of these links to connect it to each other by number of joints. So I'm going to have tau 1 and theta 1 dot, tau 2 and theta 2 dot, tau 3 and theta 2 dot, up to tau n and theta n dot, which is this picture that we started with. I don't know where, yeah, it was here. So we're going to have here a number of links. Each of them is connected by joints in between. So we're going to do the same formulation. Of course, it will be more involved because here we had only one body and we canceled the dynamics. So we reduced from 6 to 1 degree of freedom. Next time, we're going to have 2 rigid bodies and then reduce the 12 degrees of freedom into 2. So it will be just a little bit more involved. But after that, it will be just recursively. We're going to write it in a general way such that you can put it on the computer and it will do it for you. In the end, we're going to have here an equation that looks something like this. It's an m of theta multiplied by theta double dot plus c of theta and theta dot plus the gravity term, which is g of theta. If you took any course on robotics, this should be familiar to you. Okay. We just derived this for the pendulum. Of course, this term was 0. We didn't talk about gravity. So we were left only with this term, and the m here was constant. So this was the expression we derived today. The manipulator dynamics for the simplest manipulator in the world, which is just one link manipulator. Okay. So let's stop here, and if you have any questions, I can take them offline. Okay.